Before we start our discussion of Coulomb's law, let's do a quick review of some things that we know from before. Bodies consist of atoms, and atoms themselves consist of three types of particles. You have electrons, which have almost no mass and a negative charge. You have protons, which have mass and a positive charge, and you have neutrons, which have a mass but no charge. That is, neutrons are neutral, protons are positive, and electrons are negative. The neutrons and the protons are present inside the tiny central portion of the atom, which is called as the nucleus. Whereas the electrons of the atom revolve about the nucleus in orbits. Now, it's difficult to take neutrons and protons out of the nucleus, whereas it's relatively easier to take electrons out of the atom, that is, out of their orbits. So whenever we talk about the movement of charge, we almost always mean a movement of electrons. A body will become positively charged when it loses electrons, and it will become negatively charged when it gains electrons. That is, both positive and negative charges are caused by the motion of electrons. The SI unit of charge is Coulomb, which is denoted by capital C. The charge on an electron is negative 1.6 into 10 raised to minus 19 coulombs. The charge on a proton, therefore, would be positive 1.6 into 10 raised to minus 19 coulombs. This number 1.6 into 10 raised to minus 19 is what is called as the elementary charge. Every charge that exists is an integral multiple of this small e. Integral multiple means that it could be 25e, 34e, 5e, any of those values are fine. But it cannot be 24.6e, 2.4e, 7.1e. This rule that all charges exist as integral multiples of this e is what is called as the quantization of charge. Now there is somewhat of an exception to this rule. There are these particles called as quarks, which were discovered back in the 1960s, and these quarks have charges which are of the magnitude 1/3 e. Now the thing is, we would be tempted to think that this makes our rule invalid, but the point is, quarks do not exist as isolated particles themselves. They combine together to form our electrons, protons, and so on. And therefore, we still say that the quantization of charge holds true. The easiest way to charge a body is by using friction, or what is more correctly called as the triboelectric effect. What is this triboelectric effect? When you take two bodies and rub them together, what you might see in some cases is that electrons are transferred from one body to the other, making this first body positive and the second body negative. A common example of this is when you take a glass rod and you rub it with a silk cloth. You will find that the glass rod gives electrons to the silk cloth, making the rod positive and the cloth negative. This is called as triboelectric effect. Now, there's a question here. Why does this transfer of electrons happen only from glass to silk and not the other way around? The answer to that lies in the causes of the triboelectric effect. It's easy to think that it's just friction which is dislodging these electrons and causing them to move from one body to another. But that's not really true. Because if friction were the only thing doing this, then you could have electrons moving from glass to silk, but you could also have electrons moving from silk to glass. The causes of triboelectric effect are slightly more complicated than that. But the thing is, triboelectric effect is not in our syllabus, and so out here we're not going to discuss it. You can always Google it, Wikipedia it, and you should be able to find stuff on it. The next thing we need to look at is conduction. What is conduction? Conduction is the movement of electrons, the free movement of electrons from either one point to another or from one body to another. Materials which allow this to happen, that is, materials in which the free movement of electron can take place, are what are called as conductors. And materials which do not allow this free movement to take place, which impede the free movement of electrons, are what are called as insulators. Most of your metals are conductors and most of your non-metals are insulators. So out here, if you take a negatively charged conductor and touch it to a neutral conductor, what you will see is that electrons from out here will flow into this guy, making this less negative and this negative. A common misconception here is that this transfer of charge will take place until the charges in both the bodies become equal. That's not true. We will discuss that in further detail in this chapter called as electric potential. If I made this rod positive and then touched it to a neutral conductor, this rod will absorb electrons from the conductor, making itself less positive and making the conductor, the neutral conductor, positive. Induction is a different story. In induction, no real transfer of charge takes place. The charge that already exists gets redistributed. What do I mean by that? Consider a positively charged body brought near a neutral conductor. Let this guy be an insulator, helps us simplify the situation, and let this guy be a conductor. What you will see is that the electrons that are available in the conductor, it's a neutral conductor, but it still has electrons, right? The electrons that are available in the conductor to move will be attracted by this positive rod and will accumulate on this side of your conductor, making the other side positive. Note that no real charge has been transferred from this to this. That hasn't happened. The charges that were already present here have been redistributed. This is what is called as induction. The minute you take this guy away, this guy will go back to being neutral. Now, suppose that while this guy was around, I earthed this guy. What does earthing mean? Earthing simply means take a wire or any conductor and attach it between your body and the earth. Now the earth is special. The earth can give you as many electrons as you want and it can take in as many electrons as you want. That is, the earth acts as an infinite source and an infinite sink of electrons. The minute you do this, the minute you make this guy connect to the earth, what the earth will do is send in electrons to neutralize this positive charge. If the conductor was negatively charged at that end, then the same earth would have absorbed the electrons to again make that end neutral. Now note that this, what is happening here, is conduction. Because an actual transfer of charge has taken place from the earth to the body. And now, after this has happened, your body will have a net negative charge because of the addition of these electrons. What if you again had this positive guy but now had two conductors? What you would see is this side would become negative, this side would become positive, then this would become negative and this would become positive. What if you had the two bodies touching each other? Then what you will see is that they act as one conductor, so that this end of that one conductor becomes negative and this end becomes positive. Again, conduction has happened here in addition to the inductive effect. Why has conduction happened? Electrons from this body have flown into this. Which means that now if I separate these two bodies, this guy will have a net negative charge and this guy will have a net positive charge. Note that in all these cases where transfer of charge is happening, that is where conduction is happening, the net charge in the system, that is the net charge between the two bodies, remains the same. Whatever one body loses, the other body gains. This property is what is called as conservation of charge. An interesting thing to note is that induction and conduction work only in conductors. No redistribution of charge or transfer of charge will take place when you have insulators involved. That finishes our review of previous topics. Let's start with our discussion of Coulomb's law. Suppose we take two charges, Q1 and Q2. These charges are what are called as point charges. If you don't have point charges, the Coulomb's law discussion becomes slightly more complicated. So we are going to stick with point charges, that is, charges concentrated at one point. Let these 2 point charges be separated by some distance r. Now, what do these charges do to each other? They either attract each other or they repel each other. They would attract each other if they were unlike charges, that is, charges of opposite sign. And they would repel each other if they were like charges, that is, charges of the same sign, both negative or both positive. There are some things about this force of attraction or repulsion that are kind of intuitive to us. If I increase the charges, that is, increase their value, make them more charged, then we know that the force between the two guys will increase. But if I increase the distance between them, then I intuitively know that the force between them will reduce. Coulomb's law is what converts this intuition of ours into a mathematical form. What Coulomb says is that the force between these two charges is directly proportional to their product. That is, the product of the magnitude of the charges. And the second thing that Coulomb says is that the same force is inversely proportional to the square of the distance between them. What is interesting to note is that Newton said the same two things about the gravitational force, which is quite cool, seeing how you wouldn't think that gravity and the force between charges would be connected in any way, but turns out that the same law works for both of them. These two together give us F is proportional to Q1 Q2 by R square. Now, from math we know that whenever some quantity A is directly proportional to some quantity B, it simply means that the ratio A by B, or for that matter B by A, is some constant. Or in other words, the quantity A is this constant multiplied by quantity B. Applying the same thing out here will tell us that the force is some constant into Q1 Q2 by R square. What is this constant? This constant is called as Coulomb's constant. and it is special in that it has a formula of its own. Its formula is 1 by 4 pi epsilon. The first time my teacher taught me this, I was kind of irritated. The thinking was that, constants aren't supposed to have formulae. Constants are supposed to be simple guys, like the gravitational constant, just one letter, big G. The gas constant, just one letter, big R. Resistance in Ohm's law, just one letter, big R again, etc., etc. And so, it seems strange that this formula had to be defined, this constant had to be defined with a formula of its own. I mean, why do that? Why not just come up with one letter for this guy too? The thing is, as we move further, we'll realize that keeping this constant in this form helps make the formulae for a lot of other quantities much simpler. And it's like this guy is sacrificing his simplicity so that the others can be simple. Now, in this formula, we know what pi is, right? 3.1415 ... But we do not know what this epsilon is. This epsilon is what is called as the electric permittivity of the medium. What does this electric permittivity thing mean? Electric permittivity is something we'll discuss in further chapters, especially in this chapter called capacitors. But for now, it's okay to think of it as something that tells you how your medium affects the force between the two charges. Greater the permittivity of the medium, lesser will be the force. This is a bit confusing. The name permittivity seems to imply that more the permittivity, more will be the force, right? Like, more will be the permission given to the force to act. But it's actually exactly the opposite. The reason for that, like I said, we study in a future chapter. For now, just remember this. Greater the permittivity, lesser is the force. So the formula for our force is now 1 by 4 pi epsilon Q1 Q2 by R square. There is one thing we can figure out about epsilon right now, and that is the units of epsilon. If I rearrange this equation, epsilon will become Q1 Q2 by 4 pi F R square, and therefore the units of epsilon will be Coulomb square upon 4 and pi don't have any units, right? Newton for force and meter square for R square. Or in other words, Coulomb square, Newton raised to -1, meter raised to -2, which is a better way of writing units. Now, there is one standard permittivity whose value we should be aware of, and that is the permittivity of free space, that is vacuum. This permittivity is denoted by epsilon naught. The value of this epsilon naught is given as 8.85 into 10 raised to -11 Coulomb square, Newton raised to -1, meter raised to -2. All other permittivities, that is the permittivity of any medium other than vacuum, is defined in terms of this epsilon naught. That is, every epsilon is written as some k times epsilon naught, where this k is what is called as the dielectric constant, or sometimes the relative permittivity epsilon r of the medium. For any medium, you will almost never be given the value of epsilon. What will be given to you will be the value of k, that is the dielectric constant. And then using this formula, you would be able to find the actual value of the permittivity epsilon of that medium. More useful than remembering the value of epsilon naught is actually to remember the value of 1 by 4 pi epsilon naught, since that is what comes in our formula. This value is 9 into 10 raised to 9. And since the epsilon is now in the denominator, the units for this would become Newton meter square Coulomb raised to -2. For any other guy, it would be 1 by 4 pi epsilon, right? But that would simply be 1 by 4 pi k epsilon naught or 1 by 4 pi epsilon naught whole upon k or 9 into 10 raised to 9 upon k. So the formula for force again is either 1 by 4 pi epsilon naught q1 q2 by r square for vacuum or free space and 1 by 4 pi epsilon q1 q2 by r square for any other medium. These two formulae give us the magnitude of the force between 2 point charges. The thing is though that force is a vector quantity, which means that it needs to have a magnitude as well as a direction. These formulae therefore seem incomplete because they do not tell us anything about the direction of this force. Now you might think, what's the big deal with direction? Like charges repel each other, unlike charges attract each other. I don't really need a formula to tell me that. And that's right. In sums, in fact, you would be perfectly fine with using this formula for magnitude and then figuring out the direction via the like charges, unlike charges thing. But when you're stating a law, it's always preferable to make it complete. And for that, we'll now try to figure out how to incorporate direction into these formulae. To accommodate direction, we'll need position vectors. What are position vectors? Position vector actually means a vector drawn from the origin to the position of a point. But for our purposes, we will take position vectors to simply be vectors drawn between 2 points. Let's go back to our 2 point charges. Q1, Q2 separated by a distance r. The vector from Q1 to Q2 is denoted by r21. That is the position of 2 with respect to 1. The vector going the other way, that is from 2 to 1, is denoted by r12. Suppose that these charges were of the same sign, that is they were like charges. In that case they would repel each other, that is the force on Q2 would be this way and the force on Q1 would be this way. This force, that is the force exerted by 1 on 2, is denoted by F12. Whereas this F, the force exerted by 2 on 1, is denoted by F21. The way we've denoted these things makes it a little bit confusing. R21 is the position vector that runs from 1 to 2, but F12 is the force by 1 on 2. So be careful out here. Now let's concentrate on F12. F12 acts in the same direction as R21. What if I made these charges unlike charges? Then the force between them would be attractive, and in that case F12 would be directed along R12. Now, what can you say about R21 and R12? That's right. R12 is simply negative of R21. They have the same magnitude, which is R, but they have opposite directions. So therefore, can I say that in this case, in the second case, F12 is directed along negative R21? This is interesting. When Q1 and Q2 are alike, Q1, Q2 will be positive, and in that case, F12 is along R21. But when Q1 and Q2 are unlike charges, that is, one is positive, one is negative, then the product will be negative, and then F12 runs along negative R21, which means that whether F12 is along positive R21 or negative R21 depends upon whether Q1, Q2 is positive or Q1, Q2 is negative. So if I multiplied Q1, Q2 by R21, the positive and negative sign would automatically come because of the positive or negative product, which leads us to believe that if I took my force F12 as 1 by 4 pi epsilon Q1 Q2 by R square, which is its magnitude, and multiplied it by R21, the positive or negative R21 would be taken care of. But this would lead to a slight problem. This is the correct formula for magnitude, right? But by multiplying it by R21, you have changed the magnitude. And that's something we don't want. So what do we want here? We want to somehow multiply it by a vector without changing its magnitude. How do we do that? There's only one way to do this, and that is bring in a unit vector. What is a unit vector? As the name suggests, a vector whose magnitude is 1. So when you multiply a number, a magnitude such as this by a unit vector, then the magnitude will be unaffected. And therefore, instead of multiplying by the vector R21, I will multiply this magnitude by the unit vector R21. Note this little hat. A hat on top of any vector tells you that it's a unit vector. How do you obtain this unit vector? The way to obtain a unit vector is to take your original vector and divide it by its magnitude. And therefore, the final formula for F12 is 1 by 4 pi epsilon Q1 Q2 by R square into R21 bar upon R, which obviously becomes 1 by 4 pi epsilon naught Q1 Q2 by R cube into R21 bar. What would the formula for F21 be? 1 by 4 pi epsilon Q1 Q2 by R cube into R12 bar, because the two forces have to be opposite in direction. This is what is called as Coulomb's law in vector form, and it is the appropriate complete way of stating Coulomb's law. The fact that F12 and F21 are in opposite directions is immediately visible from this form. And so the fact that Newton's third law holds true here is a part of this form. The fact that like charges repel each other, and unlike charges attract each other, is also a part of this form. Because out here the directions of forces are being obtained straight via the formula. And that finishes our discussion of Coulomb's law.